Okay, so I'm just picking up essentially where we left off in class. Before we left, there was a question in the chat about how we ended up with a three-ringed structure from this problem. So I'm going to go ahead and show you how that happened. So we have two equivalents of our diene and one equivalent of our dienophile. So there's our dienophile, and then I'm going to draw the diene in a different color. Since we're reacting with two equivalents, they're going to react on either side so that each diene is reacting with a dienophile. And this isn't a dienophile just because it's an alkene. It's a dienophile because we also have these electron withdrawing groups pulling electron density away from it. So that's what makes both of these alkenes good dienophiles. And then that means that we're going to be creating bonds here, 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 and here. So that's how I got the three-ringed structure. The rest of it is just knowing the Diels-Alder mechanism. So we're going to have an attack that is concerted, all kind of happening at once, creating a double bond there. We're going to have the same type of thing happening here. And that's going to give us our new product. So I'll go ahead and draw using the same colors. None of the double bonds from the dienophile are going to carry over. None of the carbon-carbon double bonds. These are the new bonds that we made from the diene. That one went a little crazy. Okay. And then here are our diene carbons. Okay. So that's one of the products. The other thing that we discussed was that when I drew this, I chose to draw the methyl groups of both of them going up, but there's also the possibility that the methyl groups will end up going in opposite directions. So there's also a second product that is just as likely to form. So both of these products would form. And we also did not bother drawing any stereochemistry, showing directionality, because both of these substituents on what used to be part of the diene are just hydrogens, so it doesn't really matter which way the bonds to the electron withdrawing group, so these bonds, are going, because there is no endo or exo product here. We only have, two products that are equally likely to form, that are just results of different regiochemistry, essentially. So this problem we actually started in class, and we figured out the diene and the dienophile from the first one. I'm just going to go ahead and keep working through the same process here. So we highlighted the bonds that were formed in the Diels-Alder reaction in red. That's why some of the bonds are a different color. So if we imagine breaking this bond, that's going to give us a 5-membered ring as our diene. And then our dienophile has this framework of 3 carbons. So that's all you need to do. The last one is the trickier one. So we need to break these bonds. These carbons would be our diene. We know that because the alkene is still there, so we know that we need to create a diene like that. And this is our dienophile, so our alkene is right here between these two carbons. And since the substituents here are drawn trans to each other, we know this must be a trans alkene, because that is conserved from the starting material to the product. So that's all you need to do. Oops, I need some methyl groups here. Okay. Okay, so these were some problems that were on a previous quiz of mine. I put them here because they cover some OChem 1 and OChem 2, so I think they're really good practice, especially for next week's quiz, since I'm going to hold you accountable for OChem 1 material. So this first reaction, we have a double bond, and we have aqueous sulfuric acid. This is an acid-catalyzed hydration. And not that it matters, because each of these carbons are equally substituted, but this would be a Markovnikov addition. But again, it doesn't matter because the alkene is symmetrical. We're going to end up with cyclohexanol as our product. Now, the next step says, what reagent is required to go from cyclohexanol to cyclohexanone. Literally any of the oxidizing reagents that would work. So you could do a strong one like Jones, or potassium permanganate with base and heat. Sorry, that's a negative sign that's in that. You could also do chromic acid. You could do PCC. You could do Swern oxidation. Any of your oxidizing reagents that would work. Okay, so for this next one, we have a primary alkyl halide. We're reacting it with magnesium, metal, and ether. This is telling us that we are making a Grignard. So this is your OChem 2 material. So our Grignard is going to have the same carbon framework. We're not going to change that at all. And remember, a Grignard is not usually a final product. So this is the answer to this box, but this wouldn't usually be the final product of a multi-step question. But you are going to use this, which is a nucleophile. These electrons are going to attack our aldehyde. So that's what the aldehyde has been introduced for. So with this one, the big trick is to make sure that you don't accidentally add or lose any carbons. So I'm going to go ahead and copy the same carbon framework. So these are the carbons that already existed. This is my carbonyl carbon that I just made a bond to. This is my bond from my Grignard. And then my Grignard has 1, 2, 3, 4 carbons. 1 right here, 2, 3, oops, 3, 4. So I'm going to cover up that bond so it looks a little cleaner. So again, okay, here's my carbonyl carbon added on my Grignard. That's the trickier part as far as counting your carbons. This is also going to have an alkoxide oxygen and a hydrogen, because those are the other two things that are attached to this carbon. So if I were you, before I move on, I would just count, make sure I have the correct number of carbons. So there are 4 in my Grignard, and there are 1, 2, 3, 4, 5 in my aldehyde. So there should be 9 in the product that I've drawn in this box. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the fact that The fact that I have 9 carbons is a really good sign. And again, this is not usually a product. Normally we would follow this up with an aqueous acid workup, but notice that in your next step, you actually have your Jones reagents. So we have chromium trioxide, we have water, we have sulfuric acid. So this is going to protonate our alkoxide right off the bat, right? Because protonation is the fastest reaction in organic chemistry. So that's going to happen. But then we also have all this other stuff in here, right? This is still Jones reagent. So your secondary alcohol that you just created is being reacted with Jones. And you do not have to draw this in order to get this answer. I'm just showing you why there was no aqueous acid workup. It's just because it's kind of unnecessary. And then one last count just to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. The most common mistake that I saw on this problem actually was not missing the chemistry or anything. Most people did really, really well with the chemistry, but the oxygen kind of started migrating around the molecule. So people would have the correct number of carbons, but they would put the oxygen here on accident. Or, you know, they drew the alkoxide correctly, or the alcohol. I think I gave credit for that as well, even though it's not technically correct. But then after they did Jones, they put the ketone here instead. So just make sure that you're keeping track. If you know that you tend to mess that type of stuff up, it wouldn't hurt if in a quiz, if you just went through and numbered your carbons. So there's 8 in the longest chain there. And make sure that your oxygen is not migrating. So anyway, that's those 2 problems. Okay, and then in this last one, a couple of things happening here. So we have a carboxylic acid, and we haven't learned of a way to take a carboxylic acid and just turn it into an aldehyde. Later in the semester, we will actually learn that there is a 1-step reaction that will do that. But for now, the only way that we know to get from a carboxylic acid to an aldehyde is to reduce it and then oxidize it. So if we take the carboxylic acid and reduce it with lithium aluminum hydride, this is a strong reducing agent. So it is strong enough to do this reduction. We end up with this primary alcohol. Again, go through and count your carbons, especially if you're prone to losing or adding carbons. And then the question becomes, how do I go from a primary alcohol to an aldehyde? There are 2 ways that you know to do that. Both of your mild oxidants will accomplish that. So you could do PCC or you could do Swerin. In the next one, I'm actually seeing an error in the reagents down here. I wish I'd caught that earlier. These are your Swerin reagents. Okay, so in the next one, we're starting off with a Grignard, just like we did on the previous page, but we have a different target this time. Instead of a carbonyl, we have an epoxide. So a Grignard is a nucleophile, it's a base. When you attack an epoxide for a ring opening in basic conditions, is it going to attack the more substituted carbon or the least substituted carbon? Remember while you're thinking about this, that this is literally just an SN2 reaction, and in SN2, do we tend to prefer the more substituted carbon or the least? We tend to prefer the least substituted carbon. It's the easiest place for the nucleophile to get into. So it's going to attack the carbon and break open the ring, giving the electrons back to the oxygen. This is another kind of slippery slope for counting your carbons. So there are 3 carbons from the Grignard. Here's the bond that we just made. There are 3 carbons from the epoxide. I'm going to kind of draw them in the same shape as they are in the epoxide. Oops. That spot will not go away. Well, maybe it will in a second. There we go. And then the oxygen is going to end up on the middle carbon of that. And this would be the product after step 1. But notice that after step 1, we have an aqueous acid workup. So we get to protonate it to make an alcohol. Before we move on, go ahead and just count, make sure everything's there. We have 1, 2, 3 carbons from the Grignard reagent, 1, 2, 3 carbons from the epoxide. That means we should have 6 in our product here, which we do. Now in this next part, we have the Swern oxidation. This is another mild oxidation. We have a secondary alcohol. Now, secondary alcohols are super great because no matter what oxidizing reagent you use for a secondary alcohol, you're always going to get a ketone. So I'm going to draw my 6 carbons out. And on carbon number 5, I'm going to have a ketone. Now I know I didn't draw the carbons exactly the same way as last time. I was just kind of cleaning up the structure. But if you want to keep your answer clear, you can either draw your carbon framework out in the same way, or if you want to draw your carbons all in a zigzag chain, just number them. So I numbered from left to right here, even though that would not be the correct IUPAC numbering if you were trying to name it. So I would then number left to right in my product here and just make sure that the carbon or the oxygen stays on carbon number 5. So I remember looking at these quizzes, and one of the big issues was that people tried to straighten out the carbon chain and they ended up putting the ketone here, or they straightened out the carbon chain and ended up with a shorter chain somehow. So make sure that you always do your carbon accounting, because it only takes a couple seconds, but it can save you so many points. And that's it from today.